Hello guys, and welcome to my video. So today we're going to be solving the October-November question paper 1-1 for physics, and the question paper is 1 hour 15 minutes long, and I'm going to be going in detail explaining all of the questions and how they were supposed to be solved. So if you like my content, please do like, subscribe, and comment if there's anything that is unclear or any help that you would need in this paper. Okay, so to start off, we'll start off with the first question. Okay. Number 1, for which quantity is the magnitude a reasonable estimate? So this is a very, very important topic that stresses on a very important concept, which is the concept of reasonable estimates. So how exactly do you tackle this topic? Well, we just look at the answers that you're given and you sort of try to figure out which of the following answers would make sense. Okay, so if we were to start with A, basically it requires you to know the frequency of radio waves, right? So it's very hard for you to memorize frequencies, but my advice would be for you to memorize the wavelengths, and that can help you then deduce the frequencies as you'll be going on. So as you can see here, for number 1, okay, I know that V is equal to F lambda, right? That's a fact. Is something that is known, okay? The famous wave equation. Okay, so since we know this, we can therefore be able to find lambda, a possible lambda. We know that the speed of radio waves is 3 times 10 to the power of 8 divided by the frequency that we've been given here, 500 times 10 to the power of negative 12, and that should give you a lambda of 6 times 10 to the power of 17 meters. Okay, but if you've done any research on radio waves from your test book, you should have seen that radio waves basically range, okay, from 1 to about 10 to the power of 6 meters. That is basically the range of radio waves. So this answer cannot be. So A is wrong. Then if you look at B, right, we've been given the mass of an atom. How do you know the mass of an atom? You might ask. Well, look at this, right? An atom is made up of subatomic particles. And if you look here, we're given the mass of a proton. Right, you know that a proton weighs the same mass as an electron. So I'm just going to assume this is some weird element that is 50 protons, that is 50 electrons, right? So generally it is 100 things that becomes 100, okay, times 1.6 times 10 to the power of negative 27. Okay, let's go crazy. Let's say 1,000, right? 500 protons, 500 neutrons. Right, let's say 1,000 for example. This, if you calculate this is going to give you 1.6. okay, it's going to give you 1.6 7 times, also there's a 7 here, times 10 to the power of negative 24 kgs. Okay, and then if you convert this to grams, it's going to give you 1.67 times 10 to the power of negative 21 grams. Right, and this doesn't make sense. That's a very, very big answer for the mass, because you were just given 500 times 10 to the power of negative 6, right? And then if you move on to this one, Young modulus of steel, I think Young modulus is something that you should just know. I've seen a lot of questions that require a student to know the Young modulus, and my advice, just know it by head. It's usually of the magnitude of 10 to the power of 11 pascals. Okay, and if you had known that, you would have gotten that C has to be wrong. Then if you look at D, even without knowing C, right? If you look at D, we're given 500 nanometers, right? We know that visible light, okay? We know that the range for visible light basically lies from 400 to 700, right? And know that visible light consists of what? Roy, GBIF. So this means that green light has to be 400, between 400 and 700 is wavelength, and in this case is 500 nanometers. So the answer has to be D, sorry. Very important. Okay, move on. Question 2. We've been told that the speed of a wave depends on its wavelength L and the acceleration of free fall G. What is the possible equation for the speed V? Right, so this is a very important concept that I need you guys to know. Right, so it's a concept of something that is known as homogeneity. Okay, basically it assumes that the units on the right hand side, right, must be equal to the units on the left hand side. Okay, so if you check that and you find out that that's true, that in the equation that you've been given, the units on the left hand side and the units on the right hand side are equal, it basically means that equation is correct. So let's first start with A, right? So if we were to look at A, right, on the left hand side, we're given V, and the units of V are meters per second. Okay, then if you look at the right hand side, we're given the square root of, right, G is ms to the power of -2 times m, which is basically going to be the square root of m squared s to the power of -2, and that's just going to be ms to the power of -1. So the left hand side and the right hand side have the same units, meaning that equation A has to be correct. Okay, so whenever you're proving using homogeneity, you just have to prove is the left hand side having the same units as the right hand side. If they have, that means that equation has to be a possible equation. Okay, moving to question 3, we've been given two vectors, vector x and vector y, that have been drawn to scale. We'll be given that x is equals to y minus z, and we've been asked to show the diagram which best represents the vector z. So I need you guys to know a very, very important method. I always stress that you understand this method because you use it a lot in physics. It's a very famous method which is known as the head to tail method. Okay, it's the head to tail method, right? Which basically says if you're given two vectors, right? If you're given two specific vectors and you're asked to join them, you have to join them head to tail, right? For example, if I give you this vector, okay, then I give you this other vector, you have to join them head to tail. So the tail of this vector joins to the head of that vector, like so. So a resultant force is going to come from the tail of one vector to the head of the other vector, right? And then if you draw this, this is going to be your resultant. Okay, so this is going to be your resultant, basically. Okay, so if you go here, if you connect them head to tail, the resultant force must be that result. So here we want to find Z, right? I can express Z. I know that Z is going to be equal to, if I put Z on this other side, it's going to be equal to y minus x. Okay, y minus x. So it means that if I have vector y which is going in this direction, okay, so I'm going to represent vector y like so, okay, like this, right? But I have vector negative x because this, guys, can be expressed as, if you look at this can be expressed also as y plus negative x, right? This can also be expressed as y plus negative x, because if you think about it, it is basically the same vector just expressed in a different way. Okay, so negative x should be pointing down, right? They're opposite in direction, so it should be pointing down. So if we're going to take this vector, right, and using our method, I have to join the tail of this vector to the head of the other vector, like so. Okay, and as I have said, where should our resultant come from? Our resultant must come from to the head of the other vector. So the tail of this vector to the head of this other vector, like so. Okay, right, something like this. Basically that's it, right? So this is going to be your resultant force R, and in this case the resultant force represents Z. So it means that the answer which we show Z in this direction has to be A. It is the closest answer that we have to representing Z. So remember, always connect your vectors head to tail, and then everything should be okay. Question 4. A student intends to measure accurately the diameter of a wire, okay, and the internal diameter of a pipe, and we've been asked to recommend what instrument should this student use. So the student is desperate and he wants us to help him or her as physicists what instruments are appropriate. So for me, I would recommend, for you to measure the diameter of a wire, I would recommend that you use a micrometer. Okay, I would recommend that you use a micrometer screw gauge. Okay, it is pretty accurate when it comes to measuring such small diameters, especially diameter of a wire, because it is an accuracy of 0.001 centimeters, right? And then for you to measure the internal diameter of a pipe, I would then recommend that you use a vernier calipers, okay, or just a calipers to be short, which is accuracy of 0.01 centimeters. But that is more appropriate for you to measure the internal diameter of a pipe. Why? Because a calipers is, if you have a specific object, something like this, right? Like this, you just put the jaws of the calipers, you put a jaw of a calipers here, then the jaw of another calipers here, then you're just able to make the measurement that you need. So you just put your jaws on these edges, then you can therefore just be able to make the measurement. So I'd recommend for the wire, you use a micrometer. For the pipe, you use a caliper. So the answer would be C. Move on to question 5. We'll be given the power that is dissipated. Moving to question 5, we've been told that the power dissipated in a resistor of resistance R can be calculated by this expression. And we've been asked to calculate the percentage uncertainty in P. So whenever you're given division and two quantities dividing each other, we always find the percentage uncertainty in P as follows. So the percentage uncertainty in P will be equal to, since we have a power here, we're first going to multiply it by 2. So it's 2 times the percentage uncertainty in V plus the percentage uncertainty in R. And the percentage uncertainty in V is 2 times, which is 5, plus a percentage uncertainty in R, which is 2. Okay, 2 times 5 is 10. 10 plus 2, that's basically going to give you 12. So it's 12%. Okay, whenever you see a question about uncertainties, always find the percentage uncertainty in every quantity separately. If there's a power, multiply by that power. Okay, move on to question 6. The velocity time graph of an object of a mass 2.5 is shown. So I have a ball, right? As you can see over there, I have my ball. And my ball has a mass of 2.5 kgs. And then the velocity time graph of that ball, so I'm going to roll that ball. Okay, so if I'm going to roll the ball, I'm going to roll it maybe, let's say, from point A to point B. And I'm measuring the time taken for it to move from point A to point B. So basically, it's going to take me 15 seconds, right? 15 seconds. But the first velocity, if you look at this, this is 2, 4, this is 3. So it first started off with 3 meters per second. Okay, but when it finished off with 12 meters per second. So it was accelerating, right? The velocity was changing per unit time. Okay, so how do I go about this calculation, right? I just want to find the resultant force that was acting on this object for it to move from point A to point B. Maybe a person was pushing it so that it can be able to accelerate, right? So I know that F is going to be equal to mass times acceleration, right? But what do I know? I know that my acceleration is equivalent to V minus U divided by T. Final velocity, change in velocity over time. Final velocity is 12. Initial velocity is 3. My time taken is 15. And if I do my calculation correctly, that is going to 0.6. Okay, so it's going to give me an acceleration of 0.6. And then for me to then find my resultant force, it's just going to be 2.5 times 0.6. Then that's just, going to give me 1.5 newtons, right? Which is very important. So it's going to give me 1.5 newtons. So that's how you think about this specific calculation. Okay. Moving to question 7. Which statement follows directly from Newton's first law? So we have Mr. Sir Isaac Newton, very famous guy in the 17th century, I think. He came up with 3 laws of motion, very, very important. So you're supposed to know them as a physics student. The first law says that a body at rest will remain at rest or uniform motion unless acted upon by an external force. That is accurately described by A. Second law, the force is directly proportional to the rate of change in momentum. Third one, if body A exerts a force on body B will exert an equal but opposite force on body A. Right? The famous opposite and the famous action and reaction pair. Okay, but if we look at B, let's just see why the others were wrong. If we look at B, a satellite in circular motion, you don't do circular motion just as yet. But we're told that it has a constant velocity. This has nothing to do. Newton never said this. These guys are lying, right? A water drop leaving a spinning umbrella, traveling at a constant velocity, right? We have an umbrella. A water drop is leaving that. That is nothing to do with Newton's first law, right? These answers are so fun. Okay, the force acting on an object is equal to its change in momentum. No, it's equal to the rate of change, okay, of momentum, right? It's not equal to just momentum itself, right? So the answer has to be A. Very important for you to be thinking of that. Question 8. A resultant force causes an object to accelerate, okay? What is equal to the resultant force? Like I've said, it's the change in momentum per unit time. Guys, lock in. The change in momentum per unit time is basically the resultant force, okay? Question 9. A skydiver falls from an aircraft. We're given an aircraft. So we're here. I have an aircraft that is here. Okay, so this is my aircraft, right? And then a skydiver is going to fall. So a skydiver, I don't know, where is he falling from? Where is he falling to? We don't know. As physicists, we've been asked to describe their velocity and their acceleration and how it changes. Okay, so when the skydiver is here, okay, so we have our skydiver, okay, which is over here. When they're about to fall, the only thing acting on them is their weight. Okay, and since it's their weight, and I know that F is going to be equal to ma, it means that the acceleration is just going to be 9.81 meters per second squared, as they're just beginning to fall. Acceleration is just going to be 9.81 meters per second as squared, as they're just about to fall. But as they begin to fall, air resistance, okay, air resistance begins to act. Okay, so air resistance will be acting up, and as air resistance is acting, the effect of air resistance is very apparent and very, very visible. The effect of air resistance is that the resultant force, okay, is that the resultant force will decrease. Okay, and if the resultant force decreases, what does it mean? It means that the acceleration decreases. Because the force is decreasing, since F is equals to ma, the acceleration will decrease. So the acceleration is going to be decreasing and decreasing. But guys, acceleration is the rate of change of velocity. Like I've said before, is the rate of change of velocity. If there's still an acceleration, even though it's decreasing, if there's still an acceleration, it means that the velocity is going to increase, right? The velocity is going to increase because there's still an acceleration, right? The velocity cannot be constant. Acceleration means increase the velocity, increase the velocity. But if it's decreasing, just means that the rate at which that velocity is increasing is just decreasing, but your velocity will still be increasing. So as they fall down, air resistance begins to act, and then their velocity begins to the rate of increase of the velocity begins to decrease and decrease. So it means that the velocity will still be increasing, but just at a decreasing rate. That's why the acceleration will be decreasing. There'll come a point where the acceleration will be equal to 0, where the air resistance and the weight are equal. Hence, at that point, the velocity will be constant. We have reached terminal velocity. But for now, acceleration will be decreasing, but since there's still an acceleration, the velocity will be increasing, and the answer will be D. Very important for you to be thinking of that. Move on to question number 10. We're given two gliders that are traveling towards each other on a horizontal track. We have glider P and we have glider Q. Okay, the gliders have a perfectly elastic collision. What is the speed of the two gliders after the collision? There are two methods. You can either find the momentum before collision, and then using these masses, you can sort of try to prove if the momentum before collision is going to be equal to the momentum after collision. Okay, first method. The second method, which I think is relatively easier, and I really want you just to know this method very well because it's highly examined in certain scenarios where you're not given masses, right? What it says that is that for an elastic collision, okay, so the relative speed of approach, the speed at which they approach each other, should be equal to the relative speed of separation, right? So if they have a perfectly elastic collision, they don't join together, they just separate perfectly. Okay, but I know this is a very important fact that I need you to think, guys, to know. Number one, if objects move in the same direction, right, S stands for subtract. What you do is you subtract their velocities to get the relative velocity, right? Then number two, if they are moving in opposite directions, okay, if they're moving in opposite directions, what are you going to do? You're going to add their velocities, okay, for you to get the resultant velocity, right? So same direction, you subtract, opposite directions, you add their velocities, okay? So in this case, these are moving in opposite directions. This is moving to the right, then this one is moving to the left. So since they are opposite, what we do, we add. So it means that the speed, okay, the speed of approach, the relative speed of approach is going to be equal to 1.2 plus 1.8, which is going to be equal to 3.0 meters per second. Okay, so if you're going to look for the speed of separation, it must also be equal to 3.0. If you look at A, that's not 1.2 plus 0.6 is 1.8. If you look at if you look at B, that's not 2 plus 1.4 is actually 3.4. But if you look at C, that's actually 3.0. If you look at D, that's actually 4.2. So the correct answer has to be C. Remember, guys, if objects move in the same direction, subtract their velocities. If objects move in opposite directions, you just add their velocities. And it's very important for you to be thinking of that. Move on to question 11. An object of weight W is suspended from a Newton meter. When the object is completely immersed in water, the Newton meter reads P. When it's immersed in oil, the Newton meter reads Q. What is the ratio of the density of oil to the density of water? Okay, first you start off with what equation do you know? That's how you just start off with physics calculations. What equation do you know? Okay, I know that upthrust, right? Upthrust is basically equal to the density of the liquid that you're immersed in times G times the volume of the object. Right, that's basically going to be equal to your upthrust. So it means that the density, right, the density of your liquid is just going to be your upthrust divided by G times V. Okay, so what this means is that for oil, the density of oil is basically just going to be the upthrust in oil divided by G times V. And then the density in water is just going to be the upthrust in water divided by G times V. Okay, upthrust is rho GV. So the density of water will be the upthrust divided by G times V. The density in oil will be divided by upthrust over G times V. But guys, why is upthrust rho GV? I've been getting a lot of questions about that. You don't need to memorize this stuff. I hate memorizing formulas, right? I want you guys to understand, not just memorize, okay? So upthrust basically compares the force acting on an object. So if you have an object like this, right, because it's in a liquid, okay, because it's in a liquid, there's going to be a certain force that will be acting here, right? Certain force F1. Then there's going to be another force that will be acting at the bottom here, a certain force F2. Okay, F1 and F2. But you know that pressure is equal to force, okay, divided by area. So the force that will be acting on that point will be equal to your pressure times your area, right? The force that will be acting here and the force that will be acting here. So F1 will be equal to your pressure times your area. Then F2 will be equal to your pressure times your area, okay? But you know that pressure in a liquid is actually rho GV, right? Rho GH, right? The pressure in a liquid. So here you're going to have your density times G times H. Then here you're going to have your density times G times H, where H is the depth, right? H is this depth, H1, right? And then H2 is basically this other depth, H2. So here you're going to have H2. So your upthrust is basically the difference in the force. So below, your object is going to be exerting a force up. On top is going to be feeling a force down. So the differences in those force is basically your upthrust. So basically, rho G, right, H1 minus H2, right, if you just factor out. So it's going to be the force. So basically, it's going to be the force at the bottom minus the force at the top. So basically, it's going to be rho G, right, H2 minus H1. But H2 minus H1 is just the height of this object, right, times your area. It's just the height of this object because we had an area here. Okay, so you're just going to have rho G, but your area times your change in this, your area times the height is basically your volume, the volume of the object. So hence, upthrust will be equal to rho GV. The differences in pressure, on the top and the bottom, and the differences in those forces is basically going to be your upthrust. So it's very important for you to be knowing of this stuff, right? Don't just memorize it, but actually know where it comes from. Why do I say the density of the liquid times G times the volume of the object? Okay, now that we have that out of the way, now we just want to find the ratio of the density of oil to the density of water. Whenever you see a question that has to find ratios, always start from the definitions and always make that thing the definition, the subject of the formula. Then just divide, right? You simply just divide. So you're going to have the density of oil, which is going to be equal to the upthrust of oil divided by G times V, right? Over the density of water, okay? Which is just going to be the upthrust in water divided by G times V. But you know that this is basically the same. So you're just going to be left with the upthrust in oil. Okay, so the upthrust in oil over, right, the upthrust in water, right? But if you look at oil here, the weight of this thing is acting down. Oh, sorry. If you look at water, let's start with water. If you look at water here, the weight of this object is going to be acting down. But I've said upthrust compares the force acting here and here. And the force at the bottom will be greater than the top. Hence, the object will start to move up. That's upthrust, right? So we're going to have an upthrust which will be acting here, right? But this P, this reading P, is basically due to the tension of this thing, right? Due to the tension of this thing. Because the tension is basically going to be P. So that spring is going to try sort of maintain the weight of the object, and it's going to cause a certain tension. So the Newton meter just basically reads that tension, right? The same thing is going to happen here. We're basically just going to have the weight here, then we're going to have the upthrust here, then we're just going to have the tension here. So if you look at here, the upthrust plus the tension, which is Q, should be equal to W. Hence, the upthrust will be equal to W minus Q. Okay, so here we're just going to say W minus Q. Then if you go to the other one, if you look at this, your upthrust plus your tension, which is P, should be equal to your weight. So your upthrust is just going to be your weight minus P. So here is going to be over your weight minus P. And if you look at that, the answer has to be D. Very important for you to be thinking of that. Move on to question number 12, which diagram shows a couple. And no, guys, this is not a couple that you know, right? You know, this is an actual couple. In physics, you know, a couple basically means a pair, right? Still in the real life, it's still a pair, right? But in physics, it refers to a pair of forces, not a pair of people, that are equal in magnitude, right? But opposite in direction, and that are parallel. So, if you look at this, a pair of forces, equal in magnitude because they have the same length, equal in magnitude, right? Opposite in direction, one points up, the other points what? Down. Okay, are they parallel? Parallel as they can possibly be. So the correct answer is A, right? B is not, same direction. F, there's only one force. We need a pair of forces. And then F, opposite directions, yes. Equal in magnitude, yes. But they are not parallel, right? Equal in direction, yes. But they are not parallel. So it cannot be C. Okay, so don't just know why one answer is correct. Also know why other answers are also incorrect. Okay, moving to question number 13. An object of weight 120 newtons. We have this object. Is supported in equilibrium. Okay, equilibrium meaning that the resultant force is actually zero. Right, that's basically what equilibrium means. Okay, by two strings is shown. What is the tension T1 in the left in the left string? Okay, so what is the tension T1 in the left string? So okay, so what we're going to do is we're going to resolve. Okay, we're going to do some resolvations here, right? So if you're here and you're going to resolve this force, right, we're going to form a little triangle like so. Okay, so if you look at this triangle, this is the hypotenuse. Okay, then this is our angle theta. This is the opposite. So it means that this side would just be, you know, the opposite. Opposite over hypotenuse will be equal to sine theta. So your opposite would just be T1, okay, sine 70, right? So what this basically means, since this is parallel, what this just tells me is that here, okay, on this line of action, I'm just gonna have T1, right? T1 sine of 70. Okay, and then if I were to resolve this, let me label this T2, right? Let me label this T2. I'm also going to have T2 sine of 20. Okay, and then on this side, so if you're going to resolve it on this side, right, this is basically going to be T1. Right now, this is adjacent, so it's going to be cos of 70. And then on this side, we're just going to have T2 cos of 20. And since these guys are in equilibrium, it means that the resultant force is going to be equal to 0, right? And this is a very important claim because it's going to imply a lot of things. It's going to mean that the forces, the summation of forces in the horizontal should be equal to 0. So what this tells me is that T1, okay, cos of 70 should be equal to T2 cos of 20, right? So T2 is just going to be equal to T1, right, cos of 70 divided by cos 20. If you punch this on the calculator, you're just going to get T2 being equivalent to 0.364 T1. Okay, so this is basically what T2 is going to be. Then if you look at it in the vertical, right, the summation of forces, the forces in the vertical should also be equal to 0. So it means that T1, okay, sine 70 plus T2 sine of 20 should be equal to 120. But what do I know, guys? I know that T2 is basically equal to 0.364 T1. So it means that I can substitute this T2 here, right? So I'm going to have T1 sine of 70 plus T2, which is 0.364 T1 times sine of 20. That's going to just be equal to 120, right? Then I can factor T1. I'll be left with sine 70 plus 0.364 sine of 20, which is going to be equal to 120. Hence, okay, hence T1 will just be equal to 120, okay, all divided by sine 70 plus 0.364 sine of 20. So it means that T1 would just be equivalent to 113 newtons. So the correct answer, based on my calculation, has to be C. Right? So you have to be thinking about this, guys. Resolve your forces and just equate, because it's in equilibrium, the resultant force has to be 0. Question 14. When we're given a large container in an oil refinery. So we've gone to an oil refinery and we're mixing oils, and we've been told that 3 oils with different densities are mixed. No chemical reaction occurs. Come on, right? Would have been now in a chemistry lesson, okay? So the mixture consists of this, guys. What is the density of the mixture? I need you guys to learn a very, very, very important concept. It's gonna be with you all your life, right? As long as you do physics in AS, right? It is a concept that is known as the density of mixtures. About this concept, right? How do you solve a density of mixture question? Okay, so the density of mixture, the density of a mixture, right, is going to be equal to your total mass, okay, divided by your total volume, right? How much total mass do you have? Of which in this case, right, where in this case our total mass, right, our total mass is going to be equal to, if you look at it, it's going to be equal to 1,200, okay, plus 1,500 plus 4,000. So that's just going to be equal to 6,700, right? And our total volume, okay, is going to be equal to, if you go back here, let's start with A. I know that density is basically equal to mass divided by volume. Hence, my volume will be equal to my mass divided by my density. So if I start here, my mass is 1,200 divided by my density of 1,100. That's just going to give me 1.09. If I go here, my mass is 1,500. My density is 860. So that's going to give me 1.74 roughly. If I go here, my mass is 4,000 and my density is 910. So they're just going to give me about 4.396. So what does it tell me? If I just add these guys up, I get my total volume. 1.09 plus 1.74 plus 4.396. So it means that my density of mixture, guys, lock in, will be equal to 6,700 all over 1.09 plus 1.74 plus 4.396. That's just going to give me a density of 927. Okay, so think about this, guys, right? You're given a question that asks you to find the density of a mixture. Whenever you see the word mixture and you're given a bunch of calculations, find the total mass, find the total volume, divide the two, voila, you have your density of your mixture. And the answer is going to be A. Very important, guys, to be thinking of this. An electric motor produces 120 watts of useful mechanical power. So we do some work, and our useful power is that the efficiency is 60, which row is correct. So basically, efficiency, okay, efficiency as a percentage is going to be your power output divided by your power input times 100. What output do you get? What input did you put? Times 100. That's your efficiency. Okay, so in this case, you have 60, right? Being equal to, what is our power output? 120. What is our power input? We don't know. Times 100. If I divide this, I get 0.6 being equal to 120 divided by my power input. So it means that my power input is going to be equal to 120 divided by 0.6. That's going to give me a power input of 200 watts. 200 watts. Okay. But, guys, you look, I'm putting 200, but I'm getting 120. What's happening? What's happening? I'm losing 200, so heat lost, right? So heat or waste is going to be equal to my power, right, input minus my power output, right? My power input, I'm putting 200. So if I was losing nothing, I should have gotten 200 out. But why am I getting 120? It means I'm losing 80, right? I put 200, I get out 120, I lose 80. Simple as that. So the answer is D. Move on to question 16. A fixed amount of gas undergoes a series of changes to its pressure and volume. In two of the changes, no work is done by or on the gas, so basically here and here, where it's neither being compressed nor expanded. In another change, work is done on the gas by its surroundings. So you need to know this, guys. Work done by a gas, right? Work done by a gas is going to be equal to, right? Is going to be equal to your pressure. Okay, your pressure times your change in volume. Why is this correct? Again, I don't like memorizing formulas, so I'm going to teach you guys why do we say pressure times the change in volume. Okay, let's go back where we started. We know that work done is basically your force times your displacement, which is just your change in a certain distance that you've moved. You're at point A to point B. What is the work that you've done? Cool. We know that pressure is going to be equal to your force divided by your area. So it means that your force is going to be equal to your pressure times your area. So you can remove this force and then say pressure times your area times your change in extension, or your change in displacement rather. Okay, so this, guys, this, you have a certain area and you have a change in length, or you're going from point A to point B. This is volume, guys, because area times the length, you have something like this, right? If you have this length, if you have this area and then this length, your area times your length is your volume. So this is going to be your change in volume, right? So your pressure times your change in volume would therefore be equivalent to your work done. Okay, so basically, this is something that you just need to know whenever you're doing physics, and it's something that you should just be aware of, right? So once you have that out of the way, the next thing that we have to sort of look at is how can you be able to make our calculation. So work done by a gas or work done on the gas. Basically, when work is done on the gas, right, it means that the gas is being compressed, right? It doesn't want, it's being compressed, right? If work is done by the gas, what does it mean? It means that the gas is expanding, right? It's doing the work, it's busy expanding, right? But if it's being compressed, we're doing the work on the gas. So in this case, Where is it expanding? It's if work is done on the gas from the question, it means that it's being compressed. So in other words, we have a decrease in volume. Okay, so if we look at here, we had 5, but here we have 2, and then the arrow is pointing here. So this symbolizes a decrease in volume. I started with 5, I ended up with 2. So it means that my pressure at that point is 1.0 times 10 to the power of 5 times my change in volume, which is 5 minus 2 times 10 to the power of negative 4. Okay, and then that's just going to give me 30 joules. Right? Answer is C. Very important for you to be thinking of that. Question 17. An object is traveling with a speed of 10 meters per second and has a kinetic energy of 1,500 joules. The speed of the object is increased to 40 meters per second. What is the new kinetic energy of the object? Okay, so I know that the kinetic energy is going to be equal to 1/2 mv squared, right? But for me to find the new kinetic energy, I need the mass. I have the velocity, but I don't have the mass. So I'm going to rely on the first equation for me to be able to find my mass. I know that my mass is 2 times my elastic energy, kinetic energy divided by v squared. So it's basically 2 times 1,500 divided by 10 squared. That's 100. That's going to give me 30 kgs. Okay, so I have 30 kgs. So for me to find the new EK for the new object is just going to be 1/2. Its mass is 30 times its velocity, which is 40 squared. That's just going to give me an EK of 24,000 joules. And my answer is going to be C. Very important for you to be thinking of that. We have a car, a very fast car. Let's say we have a Ferrari. It's a very fast car, and it's going to exert a force of 600 newtons. The engine of the Ferrari is going to exert a force of 600 newtons to move that Ferrari by 1 meter. Sorry, by 1 kilometer, right? By 1 kilometer in 150 seconds. Wow, that's big. So the engine of a Ferrari needs to do 600 newtons to move it 1 kilometer in 150 seconds. So how do you find the power? Well, I know that power is going to be equal to my work done divided by my time taken. Okay, but my work done, right? But my work done is going to be equal to my force times my distance. So my power is just going to be my force times my distance divided by my time. Then if I look at this, my force is 600, my distance is 1,000 meters. Always put it in base units, divided by a time of 150. That's just 4,000 watts. If you go to prefixes, that's just 4 kilowatts, and the answer would be B. Moving to question 19. An extension force graph for a spring is shown. So a spring basically extends when a force is applied. A certain force is applied that causes that spring to extend. Okay, but I know that F, the force that is applied acting on that string, will be equal to the spring constant times X. So K will just be equal to my force divided by X. Okay, my force is 6.0, my X is 15 centimeters. Remember, SI base units, guys, times 10 to the power of negative 2. That's basically just going to give me 40 Newton per meter. The answer is going to be D. Move on to question 20. Wire is extended by a force. The graph shows how the extension of the wire varies with the force that is applied. Initially, a force of W gives it an extension of D. The force is then increased to 2W. This increases the extension to 2D. Okay, so initially we have a force of W that's giving it an extension of D. Then we have a force of 2W that's giving it an extension of 2D. Okay, so basically that's what's going on. Right, so we've been asked which area represents the work done. So basically, if you have a graph of force, right, of force against extension, this is going to be your graph. That's going to look like this, and then the area underneath this graph, so basically is this area, right? Basically this whole area, the area underneath your graph should represent the work done, right, to stretch it from point A to point B. So basically this is the area under the graph, because work done is basically your force times your change in extension. So the area will just be your force times your extension. But in this case, since it's a triangle, your area would therefore be 1/2 fx, right? So your work done would just be 1/2 fx, because the area under this graph is the area of a triangle. Okay, so ideally we're supposed to have a graph of force against extension, but here we have a graph of extension on the y-axis against force on the y-axis. But basically it just has to be the same. So the work done in increasing from W to 2W is basically have to be the area underneath this graph. So we start shading on this axis, right? So you're not going to go and shade this, then you're going to look for the region, right? That's not going to work. What you're going to do is you're going to shade the actual region that we want, which is this region over here. So basically this is the region that we need. And if you look at this is actually very true, because we have extension on this side and then we have force on this side. So this is going to represent our work done. Okay, so our work done is just going to be TMRS. So it's TMRS, and the answer is D. Very important for you to be thinking of that. Move on to question 21. A transverse wave on a rope has wavelength lambda and period t. The graph shows the variation of the displacement of the particles of the rope with distance in the direction of travel of the wave at time t is equal to 0. A particle x is labeled, which graph shows the displacement of the particle x with time t. So we just want to find how this particle displaces. So this particle displaces, either up or down. So basically it's like up or down, up or down, up or down, up or down, because it's perpendicular to the direction of travel of our object, right? Bearing that in mind, it's going to start at a displacement of 0. So if I'm going to measure the time of how this thing moves, it has to start with a displacement of 0. And judging from my answers, I just want to find which answer has a displacement of 0, right? So if I look at my answers, the one which we start with the displacement of 0 has to be A and C. These are the only correct answers, right? B is wrong, because when time is 0, we're already having a displacement. That's not correct. The same with D, right? Okay, so we either have A or C as the correct answer. But we have a problem. Is X going to move up first, then move down? Or is X going to move down first, then move up? Very tricky. There's no teacher on earth who's going to teach you this in their class, right? Unless you've done a similar question like this, rarely do teachers come with this concept that I'm about to teach you. How do you learn these concepts? You do a lot of past papers, you watch YouTube videos, you go online and you look for resources. But basically, the concept that I'm going to teach you is very, very important. So I need you guys, if you have notebooks, please write this concept down, because you're going to need it in answering a ton of questions that you're going to do. Okay, right. What this concept is a concept of drawing, right? Drawing the next section of a wave. That process will tell you whether X in the next phase will move down or will move up. That's basically what this whole concept is about. Okay, here's how it goes. You look at where you're starting. You're starting here. You have this particle. Right, this particle has had its maximum that it can go, right? Because this is the maximum, the amplitude that it can go. So what's going to happen next? What's going to happen next is that this particle is going to move down like this. That's what's next. That's what's next, that this particle is going to move down. But the next particle is going to have its maximum displacement, right? So if this particle is going to move down, the next particle is going to experience its nice time. And it's going to be the one at the maximum displacement. You go with that. This particle is going to be the next one. You go with that. That particle is going to be the next one. Right? It's a little bit rough, but look at it. So what this basically tells you is that since this particle was at its highest here, it's going to have its lowest here. It's going to give the maximum to the next particle. The same is going to happen here. If this was like this, it's going to give its maximum to the next particle. If this one was here, it's going to give its maximum to the next particle, because after this, it's going to go like this, right? So if you look at this, let's look at X. Let's look at X together. X was here. Is X here? No. it is clear that x has moved down to this point, right? So x is going to start at a very high point, then x is going to move down. So the only logical answer would therefore have to be C. So remember, you just want to draw the next section. If they'd given me x being here, okay, if they told me that x is here, let's say here, as you can see here, this particle has moved up. So it was supposed to be this graph moving up, right? But it's not. So x has to move down because it's clear that x has to move down. So whenever you see a question, you want to determine where would the particle move next. What you're just going to do is you're going to assume, since this particle has had its maximum, the next particle should also have its maximum, then this should also have its maximum, then that should also have its maximum, and this point should be moving down. So it's all a matter of you drawing symmetrically, right? Maximum like this, maximum like this. Everyone needs to have a maximum at some point. So if I were to draw the next section again, so if I have something like this, if I were to draw the next section, it would again be somewhere here. The next particle will have its maximum, the next particle would have the next wave, like this, the next particle will have its maximum, and something like the next wave, something will have its maximum, something like, then you keep on going. Then you can see here, x was here, it moved down further, now it's moving up, it moved up further. So basically that's how you draw the next section of a wave. Just draw the next like that, then you determine is x going to move up or is x going to move down. I hope that was really helpful. If anything's unclear, please do put in the comment section. If you still don't understand it, I might make a separate video about it, but please do comment about it if it's not clear. Okay, move on. Question 22. Which statement about all transverse wave is correct? They all have the same speed. They don't. That doesn't make sense, right? Some are water waves, some are EMF waves. They can't have the same speed. The directions are parallel. No, we know that our directions are perpendicular. Okay, they all form stationary waves. Correct. They can all form stationary waves. A stationary wave is basically a wave that consists of antinodes and nodes. So if they meet sometimes at phase, sometimes not, they're possible to form a stationary wave, right? They can all travel through a vacuum. Can water wave travel in a vacuum? No, it needs a medium for propagation. So they cannot all travel in a vacuum. So the correct answer would be C. Move on to question 23. Source S emits microwaves with a constant amplitude. The microwaves hits a screen P and are reflected. A stationary wave is formed between S and P. The wavelength is much smaller than the distance between S and P. A detector is moved at a slow, constant speed from S to P. What happens to the amplitude of the signal detected by Q? Okay, you're seeing this question and it's a bit confusing. You've never seen it before in your life. You're trying to figure out, okay, how do I tackle this question? What I encourage you to do is to read the question very slowly and pick up what you have to pick. Okay, the microwaves are constant, right? Let's first start here. They're constant amplitude. Okay, that's important, right? We don't know how, but I know that's important, right? So let's first underline this: constant amplitude, very important. The microwaves hit a metal screen and are reflected. Reflected meaning a stationary wave is formed. How did I know this? A stationary wave was formed, I've been told. The wavelengths, the wavelength of the microwaves is much, emphasis on much, smaller, okay, than the distance between S and P. If you decode what this is saying, you're done. You've answered this question. This jargon, right? So physics requires you to know a lot of concepts, and it's very important for you to be thinking about this. The wavelength of a microwave, if it's going to form a stationary wave, how do you find the wavelength of a stationary wave? Right, we have a node, it'll go like this, okay, then we have a node here, then we have another node here. So this distance, guys, this distance is basically your wavelength lambda, right? From one node, you put a node, you put another node. This distance is lambda. But I've been told that the distance between S and P is much larger because the wavelength is smaller. So it means that the distance between S, so if I have S here and I have P, it's not going to form a wavelength. It's going to form something bigger. So it's going to go like this, like this, like this, like this, right? This is one wavelength. So S and P is going to be much bigger than just one wavelength. So basically, this is how we decoded it. As you can see here, the wavelength of the microwave, which is here, is way smaller than S and P because this is one wavelength. These are actually two wavelengths. So S and P is bigger than the wavelength here. like what I've said, it means that, so if I'm here, I'm just gonna form something like this, right? So if you're gonna move Q here, I know that at a node, right, my amplitude will be equal to 0, and I know that at an antinode, my amplitude will be equal to max, right? Amplitude is maximum at an antinode and minimum at a node. Okay, so it means that if I'm gonna move Q along this line, right, it's gonna increase when it hits an antinode, right? Increase when it reaches an antinode, then decrease to 0 when it reaches a node. Increase when it hits an antinode, decrease to 0 when it reaches a node. So it's going to be increase, decrease, increase, decrease, increase, decrease, and so on and so forth. And it's going to do that regularly because it's constant, right? Maximum 0, maximum 0. That's regular, right? You wake up, you go to sleep. You wake up, you go to sleep. That's a regular routine. You increase, you decrease. That's regularly because it's max and 0. So the answer has to be B. It can't just decrease steadily. It can't just increase steadily. It can't just remain constant. It has to increase and decrease. Okay. We're given a police car, right? And the siren of that police car, as it goes, is emitting a 140 hertz. A stationary observer, however, hears sound of frequency 494 hertz. The speed of sound in air is 340. What could be the speed and direction of a movement of the car? Right, maybe the observer is a robber, right? They came to rob a bank, then they hear a police car, moving. They're now, I don't know, they're now scared. They don't know what to do, right? They're just stationary. So they're going to hear a frequency of the car that is higher than the frequency that it's emitting. That can only tell me that it's moving towards, because it's only towards when you're going to have a higher frequency, right? This is the Doppler effect. The Doppler effect equation says that my observed frequency is going to be my frequency of the source times velocity of the sound over the velocity of sound plus or minus the source, right? But if you're moving towards, it's going to be V minus Vs, right? If you're moving away, it's going to be V plus Vs. Okay, so it means that my observed frequency is 494, and if we establish that they're moving towards, because the frequency is increasing, right? So 494 is going to be equal to 440, right, multiplied by 340 divided by 340 minus Vs. Okay, so it means that if I were to look at this, it means that now I have 494. Okay, I have 494 divided by 440 being equal to 340 divided by 340 minus Vs. So I'm going to have 340 minus Vs multiplied by 494 divided by 440 being equal to 340. So it basically means that 340 minus Vs should be equal to 340 divided by 494 divided by 440. So if I were to do my calculation here, I have 340 minus Vs being equal to 302.834. So Vs should be equal to 37 meters per second. So my answer is going to be 37 meters per second directly towards the observer. Is going to be A. Move on to question 25. An electromagnetic wave has a wavelength 138 picometers in a vacuum. To which region of the electromagnetic spectrum does this wave belong? Okay, I know that I know that for wavelengths, you're just going to have to memorize this. There's no way you're going to be taught or you're going to be given this in an exam. You're just supposed to know the ranges of wavelengths by head. But basically, we have 138 times 10 to the power of negative 12. That's pico, right? So that's going to be 1.38 times 10 to the power of negative 10 meters. If you open your textbook, you're going to see that the wavelength, right? The wavelength for X-rays, okay, is basically just going to be somewhere from 10 to the power of negative 9 to 10 to the power of negative 12. So basically, this is from your official Cambridge textbook. So it's basically going to give us so means 10 to the power of negative 10 basically falls in this range, right? There are multiple answers that you can find, multiple ranges, and you're going to get on the internet. But what's important is that are those ranges the same? For example, there's this one again on the internet, which is 10 from -8 to 10 to the power of -11, right? So usually Cambridge will give you a question that has an answer that will lie specifically in that range, right? It can't be ambiguous, where you can be like, does it lie, does it not? It's going to give you answers that are very clear and very straightforward. So in this case, it's going to be X-rays. Move on to question 6. Two wave pulses are traveling towards each other on a rope that is long. The pulses have the same amplitude and wavelength and traveling at a speed of 0.50. Okay. Which diagram shows the rope at a time t is equals to 3.0. Okay, what do you know? Always start with what you know. You know that the distance that is traveled, right, is equal to your speed times your time. Okay, and your speed in this case is 0.50. Your time is 3. So the distance that will be traveled is going to be 1.5 meters for both waves. So if I have a wave that is here, it's going to travel 1.5 meters. So this is 1 meter, 1.5 meter, right? So it's going to go here. Okay, going to go to this point. If I have this one, 4.5, it's going to travel, right? 4.5, this is 1, up to here, like so. If I have 4.0, like so, like so, like so, it's going to travel until it reaches here. So we're going to have at 4.5, going to go here. At 4.0, it's going to go here. Right, so basically this is what's going to happen. Then if we were to draw our waves, right, it's basically still going to be the exact same wave, something like this. This other wave here, it's going to do the same. At 7.0, it's going to move 1.5. So this is 1, 1.5. It's going to arrive here. This one is 7.5. This is 1, 1.5. It's going to be here, right? And then this one is 8. This is 1, 1.5. It's going to be here. Then if you're going to draw this wave, it's going to be something like this, something like this, something like this. Now this is getting interesting. We have two waves that have converged. They have arrived at a specific point. So what's going to happen? They're just not going to remain the same. They're going to add up to each other. So we're just going to form one big wave. Here they add up. 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 So we're just going to form one big wave that is going to be present at the middle. So we're just going to look for an answer which is one big wave, which is constant because they have the same amplitude, right? So it's one big wave, constant here, constant here. So the answer will be C, right? One big wave which is constant throughout. It can't be A, it can't be B, and it can't be D. Okay. Move on to question 27. We'll be given water waves of wavelength lambda that are incident normally on an obstacle with a narrow gap. So the gap is narrow, right? So this gap is narrow. And that's good. The smaller the wavelength is, as you can see here, this gap is almost comparable to the wavelength, right? So the more the gap is actually equal to the wavelength, the more pronounced diffraction is going to be. Okay. If the gap is slowly widened, so we're going to widen this gap. Well, let's do some physics and let's widen this gap. So the gap is going to be widened like so. Okay, like so. So we have sort of widened our gap. Now our gap is somewhere here, right? What changes will occur, if any, to theta and to the wavelengths? Guys, will this wavelength ever change by us reducing the gap? It will never change. So the wavelength is just going to remain the same, So the wavelength is just going to remain the same. But the biggest trick to this question is understanding what will happen to theta. Let's take a step back and ask ourselves, what is theta? Theta measures how much diffraction has occurred, sort of a measure of diffraction. And if I were to look carefully, look at the reference frame. Your theta is measured from this extent to that extent. Your theta is basically measured as to how far the diffraction has gone, right? If you look at it, because your theta is measuring, this is the maximum it can go. So your theta is just measuring the maximum line. So your waves are going to diffract until they reach this point. Your theta is just going to measure that. So if the gap is going to be bigger, like I've said, if the gap is very small, a narrow gap means that we're going to have greater diffraction because we're going to have a gap that's almost closer in comparison to your wavelength, right? Diffraction is going to be less pronounced. So it means that in this case, since there's going to be a bigger gap, diffraction is going to be less, right? Less diffraction. And what this means is that our wave is no longer going to spread into this region, right? Because diffraction, less diffraction means your wave is not going to spread everywhere, right? So what this means is that your waves maybe gonna spread just up to here, and all of this is gonna disappear. What? Why? Well, diffraction is not gonna reach that region, right? And all of this is gonna disappear because it's not gonna diffract enough to reach that shadow, to reach that region. So, like so. So what this means is that your angle theta is now gonna start from here, okay, to here. This is your angle theta, guys. And if you look at it, the angle theta has actually decreased, right? This angle theta has decreased because the diffraction that you're now measuring is smaller, because the angle theta is smaller. If you're still not convinced, let's go a little bit. Let's say the diffraction is really, really small. That's when you can actually start appreciating that theta is small, right? So let's assume that our diffraction was like this, right? It was this small, like this, right? This was the only diffraction that we're seeing, right? It would mean that if you think about it, it would mean that this is your line of reference, and then this is your line of reference, and then this is just your angle theta. Look, theta is so small, right? But if your diffraction was very big, if your diffraction was from here, right, all the way to here, all of this would have been your theta. If that was your diffraction, all of that would have been your theta. And hence, in that case, your theta would have been so big, right? If you look at this, if this had been all of your diffraction, right, like so, then this would have been your angle theta. But because your diffraction is small, it means your angle theta is also going to be small. So the angle theta is going to be decreasing. I hope that made sense, right? So it came from us understanding what exactly is this angle theta, right? This angle theta just basically measures the extent of diffraction. If the gap is widened, less diffraction, meaning that I'm going to have a smaller value of theta because it's going to spread less into this gap. If the diffraction was bigger, theta would increase because theta, let's assume, is going to spread here. Let's assume it's going to spread here. So basically, your theta is going to be increasing, right? I hope that made sense. If there's still questions that are unclear, please do put it in the comment section below. Okay, moving on to question number 28. Light of wavelength 720 nanometers from a laser X is incident normally on a diffraction grating, okay, and a diffraction pattern is observed. Light from a laser is then also incident normally on the same grating. The third order maximum due to laser Y is seen in the same place as the second order maximum due to laser X. What is the wavelength of the light from laser Y? Again, guys, underline important facts. That will make it so much easier. We have light of wavelength 720, and that's from laser X. Okay, and then we have light from laser Y. Right? What else do you see about laser Y? We have the third order maximum due to laser Y. Then for laser X, we have the second order maximum, right? And then I've been told that it is the same grating. Underline, guys, underline very important facts. I'm told that it's the same grating. So the same grating has implications. The third order of Y being at the third order has implications. It being a second order, that also has implications. And we're going to write that, and then we're just going to make our calculations. So let's first start with X, right? And let's get to it. Let's enjoy some physics, right? Okay, so if you start with X, I know that for diffraction grating, d sine theta is going to be equal to n lambda. Physics is very interesting, guys. Then if you go to laser Y, we're still going to have the same claim. D sine theta is going to be equal to n lambda. Okay, d we don't know, right? And we don't need to know. Sine theta, we don't know, and we don't need to know. Why? Because if the third order and is at the same place as the second order, it basically means that if it was going to diffract, right, it has arrived, this is the third order, but for the other light, it is the second order, right? So basically it doesn't matter because it means that theta would just be the same, right? Because we're just getting different things, right? For blue light, when we're at this point, it's appearing to be the third order, right? It looks as if it's the third order, but for other ones, it will be the second order, but it will still be the exact same theta with the reference from the central fringe. Okay, so it means that the theta will not change. I hope that makes sense, guys. So it means that in this case, d sine theta will also be equal to n lambda, in the same manner that this is also equal to n lambda. And this means that d sine theta will be equal to, for laser x, we have second order, so it's 2 times 720. And then for this other guy, we have d sine theta, which is going to be equal to 3 times lambda. Right? This and this are the same, so we can equate 2 times 720 should be equal to 3 times lambda. So my lambda should be equal to 2 times 720 divided by 3. So my lambda will be equal to 480 nanometers. Very important for you to be thinking of this. So we're just making deductions, guys. If the third order are in the same place, means that theta is the same. If it's the same grating, d is the same. And then we just equate that. We can then be able to find lambda. Question 29. Monochromatic light of frequency f is incident on a diffraction grating of spacing d. So if a diffraction grating, that is spacing d. The speed of the light is c, which expression can be used to determine the highest order of intensity maximum produced by the grating. All right, guys, this guys really loved gratings. Okay, so for gratings, we know that d sine theta is basically equal to n lambda. Okay, so in order for us to get n, we know that n will be equal to d sine theta divided by lambda. But the famous grating equation, the famous wave equation, sorry, v is equal to f lambda, so c will be equal to f lambda. Therefore, lambda will be equal to c over f. Hence, I'm going to have n, in this case, I'm going to have n being equal to d sine theta divided by c over f, right? Why c over f? Because, well, if you think about it, that is lambda. Okay, so that f is going to flip, so my n is going to be equal to d sine theta times f divided by c, right? But I've been told that it's incident on the grating, and then I want to find the highest order. So for diffraction, the highest order is likely to occur usually less, usually get a fraction or a decimal, meaning that you just take the whole number, right? But the highest order is always when we have sine 90, right? Because it's going to diffract, right? It's going to diffract here, maybe an order of 3. But when it's like this, when from the central fringe, when theta is 90 degrees, that is the maximum that you can go. If you go like this, then you haven't diffracted, right? You have to go in, and then you measure relative from the central fringe. And the maximum you can go is when theta is goes to 90. So we're going to have sine 90. That's going to be our maximum angle for us to get the highest order of diffraction that can be possible. I hope that makes sense, guys. So we're going to have this is going to be equal to d sine 90 times f divided by c. But sine 90 is essentially equal to 1. So I'm going to have df over c. That answer is going to be b. Very important, guys, for you to be thinking of that. Question 30. A metal plate of uniform thickness is connected to a cell as shown. Okay, electrons move clockwise. Clockwise is basically like this, because electrons are always at the negative. So electrons are going to move like this. So this, guys, is clockwise. Right? So that's very important for you to be thinking of that. So they're going to move around the circuit, and we statement about the metal plate is correct. The average drift, whoa. Whenever you see the word drift, right, number density and all that stuff, one equation and one equation alone should come to mind. I, is equals to, I is equals to AN VQ. Some textbook might say E, right, just a difference in notation, where A is the area, right, the certain area that the current is moving towards. So this is the area, and then this is the number density. Okay, the number density, and then this is the drift speed, and then this is the elementary charge. Guys, 1.6 times 10 to the power of negative 19. Lock in. The elementary charge rarely ever changes. So this is the famous equation that we have, right? I is equals to NAVQ, right? And I need you guys to always be thinking of this equation. It's going to pop up multiple times in your exam. I is going to be equal to NANVQ, okay? So if I look at this, the average drift velocity of the conduction electrons decreases as they move from left to right, right? If I look at this, N is going to be constant, right? I is constant because everything here is in parallel, right? So I is basically just going to be constant. Why? Because everything, is in series. So I is going to be constant because everything is in series, right? And based off that fact, I is constant. Q, the elementary charge, is basically just going to remain constant, right? And then N is the number density, and that is just also going to be constant. Why? It doesn't change, right? For this specific metal, the number density doesn't change. It's more like, think of number density as the actual density. Does it matter if you have a circular plate of copper, a square plate of copper, something like this? Does the density of copper actually change? Think about it. The mass that you take and the volume that you take will always give you the same density, right? So in the same case, the number density measures the number of conduction electrons per unit volume, and that will never change, right? So it means that the number density is going to be neutral, and so it means that C and D are going to be wrong on this regard. So we're going to have a relationship between A and V, right? And from this relationship, we can see that A will be inversely proportional to V. So if you're moving from here to here, right? If your clockwise is from right to left, right to left, right to left, you're going to see that the area is actually decreasing, right? So if the area decreases, it means that V has to increase. The area is very small, so the electrons have to move fast and fast and fast. They know that the area is small. So all of the electrons are now in a queue. They say, move fast, move fast. We also want to pass. So the electrons are going to move very fast. So the average drift velocity of the conduction electrons is therefore going to increase. And your answer is going to be B. So it's very important for you to be thinking of that. Move on to question 31. The diagram shows the direction of current in a metal block. The charge carriers enter the block through face P, Q, R, S. So they're entering through this face, right? So basically, this is what they're using to enter. Okay, so we just want to find the current in the block. Which expression gives us the current in the block? Like I've said, guys, look in. I is equal to ANVQ, or some textbooks might say E. In this case, they've actually used E, so it's ANVE. Then the area is just X times Y, right? So it's going to be X or Y times N times V times E. So it's just going to be INVU, right? Sorry, INVX, right? INV XY, right? So it's going to be B. So you just use that equation, then you make the correct substitutions. Moving on to question 32. What could not be a unit for potential difference? So do you know the units for potential difference? If you do, then you can be able to eliminate. So what do we know? We know that V is basically the work done per unit charge. Okay, V is equals to work done per unit charge. The units for work done is kg m squared s to the power of -2, because it's force times distance. The units for Q is AS. So it means that here I'll have kg m squared s to the power of -3 a to the power of -1. So let's test. Let's test if all the other units are going to give me this exact answer. If they do, it's correct. Okay, so let's start with A. If I start with A, I'm going to have a resistance. The ohm is going to be V is equals to IR, right? So resistance is going to be V divided by I. So you just take that same units, kg m squared s to the power of -3, then a to the power of -2, right? Times A. Times A, that's going to be kg m squared s to the power of -3, a to the power of -1. They're equal. So A is wrong because the question said not. Be careful. If you didn't read the word not, that's why they're putting it in bold. Cambridge is really kind. They say, let's put it in bold so that a person does not get confused. Okay. Then if you look for B, the N is kg, M s to the power of -2, M to the power of -1, C is A to the power of -1, S to the power of -1. So that's going to be kg, S to the power of -3, A to the power of -1. And that's wrong. So the answer has to be B. And we stop. We don't need to do C. We're not trying to prove any point. Time is not on our side. We also don't need to do D. Right? We have arrived at B, and we have shown that we are true that B cannot be equal to the units for potential difference. Then B has to be wrong. Okay? Very important for you guys to be thinking of this. 33. Which graph could show how the resistance R of a filament lamp varies with the applied potential difference PD as V is increased to the normal operating PD. Okay. What do you know? You have seen this graph popularly. I like this graph a lot. Like this, right? There's a very popular graph, a graph of I against V for a filament lamp. So basically a graph like this, right? And then if we're to flip the axis, because this is basically V against I, if we're to flip the axis and say I, if we put I here and V here, right? It's just basically the exact same graph like so. Like so, right? Basically the exact same graph. I've just flipped the axis. I put V here, I've put I here, I've put I here, I've put V here. Right. I know that V is equal to IR. I know that V is equal to IR. Therefore, R is going to be equal to V divided by I. So the ratio of V over I is R, which is basically the gradient, right, of this graph. And then if you look at the gradient of this graph, it's actually increasing. The gradient increases. Okay, and what does this tell you? It tells you that the resistance, guys, should also increase. Okay, so it means that the resistance should increase. Why? If you know the graph of a filament lamp, I would advise you go in your textbook, and if you read it, you'll find the graph of a filament lamp, right? Then if you have a graph of the filament lamp, it's always I on this axis and V on this axis. If you were to flip those axes, your V will be on this side, your I will be on this side, your graph will just change orientation, right? And then the resistance is going to increase because the resistance is the gradient, and the gradient of this graph is increasing. So D is wrong because the resistance is actually decreasing. C is wrong because the resistance is actually constant. The battle is now between us choosing which one is correct between B and A. Okay, what are the key differences here? Well, the trend, we don't really need to know about it, but the biggest difference is R here. We have a value of R, but we don't here. We have R is equal to 0. Okay, here it's a claim that the resistance for a filament lamp can actually be 0, and that's wrong. And I'm going to explain why. Do you know what resistance is? If you did, it would be much easier to explain why it's not 0, but you don't need to. That's why we're here. Let's redefine how physics is taught. Okay, so the resistance is a physical property of a material that measures its resistance to the flow of current, right? For electrons, yes, you might say. So the resistance is saying current wants to flow, but an object is going to oppose that motion. That is basically what resistance actually is, right? But the resistance can never, ever be 0. There are some instances where it's 0, yes, but for a filament lamp, it can't be 0 because it's measuring how much the filament lamp can resist, right? By us pushing a current, we're just measuring, that effect. But a filament lamp doesn't lose its resistance when there is no potential difference across it. When V is 0, a filament lamp doesn't lose its resistance because resistance is an intrinsic property. It's an inbuilt property of a material. If you go to your lab, right, and if you open a drawer, you're going to see a bunch of resistors that are labeled 2 ohm resistors, 5 ohm resistors. What is that label telling you? It tells you that there's a resistance present in that thing, right? But that thing is not connected to any circuit whatsoever. But it's written 5 ohm, one is written 2 ohm. Why? Because resistance is a property of that material, right? So the resistance is actually there, but there is no potential difference whatsoever, right? So the resistance can never be 0, meaning the answer has to be A. But there can't be a point where the resistance is 0. And if you still don't get it, think of it this way, right? You have a police, right? A police, what police do is that, let's say there is a highway or cars are moving very fast. Police tries to stop the cars, right? They try to stop the car from moving. A lot of cars are moving. Police are trying to stop the cars, right? Police have the ability to prevent, or the ability to resist the motion of the cars, and the cars in this case are the electrons, the current that is moving. So police are acting as resistors. They are resisting the motion of the current, the motion of the cars, or the motion of the electrons, as you may, right? But if there's no car flowing in the road, do the police lose their ability to resist the motion of the cars? They don't. Right? It's only that when there are cars that we can actually see that, oh, these guys have this ability, right? But when the cars were not there, they still had that. It just wasn't exercised, right? So that's the same way, right? A filament lamp will have its resistance, but it's just not exercised because there's no need to when there's no current or when there's no potential difference. But the resistance will never be zero, right? It's a long way to explain, but I hope that made sense so that you can really understand what resistance is, because resistance is equal to rho L over A, right? If you have the resistivity, the length of an object, and the area, you can therefore be able to measure it. Someone might say, well, with V is equal to IR, right? If V is 0, yes, I can be 0, but that doesn't mean R also has to be 0. R can be 20, but if I is 0, V will be 0 either way, because V from Ohm's law is directly proportional to I, but it doesn't say anything about R. If V is 0, I is 0, sure, but R doesn't need to be 0. It shouldn't be 0. Right? It can be any value it wants, but it has to be a constant value because the resistance has to be constant. Question 34. On which conservation law do Kirchhoff's laws depend? First law depends on charge. Second law on energy. The answer is B. Question 35. The diagram shows a circuit. Which statement about the circuit is not correct? EMF is the energy transferred per unit charge. That's correct. It's transferred from chemical potential energy to other forms when the switch is closed. That's correct. The EMF is greater than the terminal PD. That's correct, because some of the energy is used in overcoming internal resistance, so the terminal PD will actually be a little bit less. Okay, but when the switch is open, the voltmeter measures the EMF. So this voltmeter, this is measuring the terminal PD, right? This voltmeter is measuring the terminal PD. If it was supposed to measure the EMF, it was supposed to be here, then it would make sense, right? But here there's nothing, so it's measuring nothing. It's measuring 0. The voltmeter will read 0. So D is not correct. In this case, D is correct because that's the correct answer. Question 36. The diagram shows a circuit of 4 voltmeters. The reading on voltmeters are V1, V2, V3, and V4. All readings are positive. Which equation relating the voltmeter readings is correct? Okay, if you look at this, we know that for a voltmeter, since it's in parallel, right, V2 should be equal to V3 plus V4. So if you were to add V3 and V4, it's going to be equal to V2 because they are in parallel. Okay, so it means that V3 plus V4 minus V2 should be equal to 0. So the answer has to be D. So V3 plus V4 should be equal to V2. So V3 plus V4 minus V2 should give you 0 because they are essentially supposed to be equal. For question 37, we've been asked to find the current that is flowing through the 3 ohm resistor, right? We've been given the potential difference across the network being 4. We've been given 3 ohm resistors and 2 6 ohm resistors. Okay, so we just want to find the current, right? I want to find the PD that is over here, right? So basically, if I have V over here, I know that V is equal to IR. So if I want to find I, I should just say V over R, right? But for me to find V, I need to find how much does this get, right? So if I look at the resistance of this connection, it's going to be 1 over 6 plus 1 over 3 to the power of negative 1 because they are in parallel. So this is going to give you a resistance of 2 ohms. Okay, so for me to find my potential difference across that is going to be 2 over 2 plus 6 times 4. So basically that's going to be the PD that I'm going to get, and this is going to give me 1 volt. So it means that the PD across this is 1 volt, across this is 1 volt. So for me to find I, it's just basically 1 over 3, which is 0.33 amps. and the answer will be C. Move on to question 38. In the circuit shown, all the resistors are identical and all the ammeters have negligible resistance. The reading A1 is 0.6 amps. What are the reading on the other ammeters that are present? Okay. Let's see. If we look at this, these things are in parallel, right? This, and this. All of these are in parallel. So what this tells you is that basically the potential difference V that will be here, right, will be equal to the potential difference V that will be here, and it will be equal to the potential difference V that will be over here, because they are in parallel. Okay, here I have a resistance R, and here I have a resistance R. Here I'm going to have a total effective resistance here of 2R, right? So to find this V, I know that V is equals to IR. It's going to be IR. But then I know that my I here is 0.6 because I've told that A1 is 0.6, so I'm going to have 0.6. But what is my resistance here? It's 2R. So my resistance here is 2R, so I'm going to have 1.2R. So my voltmeter reading is going to be 1.2R across this. Then if I move here, it's still going to be the same voltmeter reading. Get this, guys? I found my V by saying IR. I is 0.6, then the R is 2R. Then here, since I'm going to have R here, my I is going to be just equal to V over R. My V is the same, which is 1.2, right? 1.2R divided by R. So it means that A3 is just going to be 1.2, right? So A3 is just going to be 1.2. Okay, if I want to find A4, again, I will just be, my V is 1.2R. Then my R is going to be R is going to be 3R. So I'm just going to divide by 3R. They're just going to give me an I of 0.4. An I of 0.4. Okay, so but I know here they're going to branch, so I want to find in A2. So here I'm going to have 0.6, right? So for here, since I have 1.2 here and 0.4 here, I'm going to have 1.6. That's going to be combining here. So 1.6 plus 0.6, that's just going to be 2.2. So for A2 is going to be 2.2, and my answer will be D. So get this, I had a V here. My potential difference across here was IR, and that's 0.6 times 2R because the resistance is R, right? And I'm going to get 1.2R. Then I'm going to find the PD across this, which is going to be the same, divided by the resistance. I get I. I do the same here. But then I apply Kirchhoff's first law to then find the effective resistance that will be through A2. Then it will be 38. It will be 2.2, right? Moving on to 39. An unstable nucleus, okay, of an element decays by emitting alpha particles and beta particles to become the nucleus of a different element. It is also unstable and emits an alpha particle or a beta particle. The process continues until an isotope is produced. So if we're going to start with, let's take a random thing, 20 and 10, and this is X. If it undergoes alpha decay, it's going to be 16. This is going to be 8 X plus 4 2 HE. If it undergoes beta decay, it's going to be 16 9 X plus 0 negative 1 and beta negative. If it undergoes another beta negative decay, 1610 X 0 negative 1 and beta minus. This is an isotope, same number of protons but different number of neutrons. So we have how many particles have we emitted? 1 2 3, and the answer will be B. The last question. The diagram shows the quark composition of 4 hadrons. One of them has a charge of plus E, and that's sigma plus, where E is the elementary charge. Which hadron could possibly be sigma plus? So if you just look at these answers, we just want to find which combination can give you plus E. If you look at this, an up quark has 2 over 3 E. Is another up quark plus 2 over 3 E. A strange quark has negative 1 over 3 E. Then this will give you E plus. So the answer plus E. So the answer has to be D. So you're just combining your quark combinations for you to be able to answer. Thank you guys for watching this video. I hope it was really helpful, and I'll see you in the next one.